Hello, Alex.
Real quick. I think it needs to be enabled by the host. Can you please enable it for me?
It's done. Yeah, please. Sorry.
Okay, here we go. So here we go. Second desktop. And let me go full screen. Great. So you should see my camera and my screen, and thank you for joining this session today. I'm Alex, I'm from Italy, and that's why it's 11 a.m. here. I'm here to tell you everything about performance tuning and cost tuning your AWS Lambda functions. I think these two topics are very interesting together because very often in the traditional compute world, they are kind of variations, right? If you want to optimize for, so pretty often these two are opposite to each other, or you have to pick one. And I really like that in the world of serverless, it's not true. It's very often, especially in CPU workloads, can have both. You can be faster and you can be cheaper at the same time. And I'll show you some data later. So this is what I like to talk about today, some fundamentals. You guys are the Solus folks. I'm sure you are already using Lambda for a while. It's been up there for more than 5 years. But just to make sure we are all on the same page, I'll share some fundamentals also related to performance and some of the internals. Then I want to share some of the best practices related to optimizations. And there are a lot of different optimization possible. Pretty often you want to go and re-architect or restructure your workload for optimal results. And I'll try to focus on the function optimization aspect of things. There is a lot more, and maybe we can discuss some of those topics as well. If you have questions at any time, feel free to jump in and ask me anything, okay?
Fantastic, yes.
Great. Then I want to propose a data-driven approach that I have had in my mind and in some open source project I've been working on. And then I'll show you some real world data and some patterns that might help you think of the performance tuning and cost optimization for your own functions. So let's get started with fundamentals, or let's make sure everyone's on the same page as far as Lambda and function as a service and serverless. This is what our CTO of Amazon, what he used to say about serverless, about Lambda. As developers, what we want really is being able to focus on the business logic, and that was Lambda allows you to do. And there are many ways, 5+ years later, to build service applications. Lambda is pretty often involved in your service applications. It's not always there though, right? Sometimes you have API gateway, or you have Kinesis, or you have I don't know, Cognito, and there is a whole serverless platform, serverless ecosystem of different services that you can pull together to design your architecture. If we focus on Lambda for a second, this is the anatomy of a Lambda function. You have your own function that ideally is taking care of one thing very well, aligning to the microservices approach. Everything is event-driven. Every time your function gets invoked, you get an event, you get a context, and you can use that to react to those events. In this example, it's a Python Lambda function where you see there is a handler, which is basically the entry point. You could have a very similar situation with Node.js or .NET or Ruby or Java, or basically all sort of languages. I've met customers in the last couple of years who have been using Lambda with Fortran code, or with code that used to run in their mainframe. So we've seen a lot of different, a lot of diversity related to programming languages. But yeah, here I'm using Python. I mostly use Python and JavaScript. If you have questions about languages, let me know later. But this is more or less the anatomy. if you look at what your files are organized, you typically have your handler, which is the entry point. Up there, you also have everything about dependencies and configuration management, maybe some common, you need to initialize some libraries, you need to initialize some shared parameters that you're going to use in your handler and in your different business logic. Then you might have other common helpers, stuff that you do pre-handler or post-handler. This also depends on how you decide to structure your code. And then you typically have the actual business logic. My suggestion here is to separate the business logic from the handler, so you can much more easily test your code and reuse your code across different compute platforms. If you organize your code well, this is pretty straightforward. And if you do it very well, you will end up spending most of your time developing business logic, which, like we saw with Werner Vogel's a couple of minutes ago, that's what we want to do most of our time as serverless developers. And then your application grows and you have tons and tons of functions. Ideally, for example, if you're building a web application with a web backend, you might have different functions to handle different domains or different endpoints. So ideally, each endpoint has its own function, right? Its own function with its own dependencies, with its own business logic, with its own database. If you want to do things right, ideally every microservice should have its own table or its own database. So you can build independent, scalable, fault-tolerant microservices. There are cases where you want to share things across functions. For example, if we're talking about parameters or secrets or tokens that you really want to share across functions, because that's part of the application, maybe some external API endpoint or some S3 bucket configuration kind of stuff. You can use the secrets manager, or you can use the system manager parameter store, for example, to share common parameters. And if we now focus on each individual function, what needs to happen as far as performance and internals is that whenever your function gets executed, there are a few things that need to happen. So everything that you see on the left side, we need to download your code, we need to bootstrap a new micro VM, and then we need to kick off the runtime on this micro VM. Okay, all of this happens transparently to you, but it still needs to happen. And everything on the left-hand side, AWS is trying every single day to optimize for you. So all the internals, all the networking stuff and privacy and security, that's our responsibility. Everything on the right side, actually, pretty often you end up using a native runtime. So also the runtime it should be on the left-hand side. But if you're providing a custom runtime, you can work on optimizing the custom runtime and your code, your business logic. So everything that is not your business logic is meant to be a cold start. And that happens every now and then. It's okay. It's the very small minority of your executions of your Lambda invocations. In some scenarios, it's very important to be able to optimize those cold starts, because that might be a few hundred milliseconds in some cases where you have a lot of initialization stuff, and I'll tell you what you can do to minimize it. That cold start might be even a few seconds. So if it's a public API, if it's a customer-facing Lambda function, you may want to optimize that cold start as well. But I always like to remind customers that you pretty often want to focus on the largest majority of invocations, which is the warm starts. We can focus on optimizing that part as well. If you want to have a better understanding of what's a cold start, what's a warm start, when does it happen, how often does it happen in my code, for example, you can look at X-ray traces in your function. You can enable X-ray with a couple of clicks in the console, or with CloudFormation or Terraform. If you want to trace HTTP calls or SDA calls, you can easily include like a simple wrapper in your handler to use the X-ray SDK. That's really, really simple. It's not included by default in the Lambda environment, so you need to kind of inject it and include it in your deployment package. But it's pretty straightforward. And here, as you can see, you can have a look at the initialization time and where is the time spent in your Lambda execution. Are we spending a lot of time waiting for an HTTP response or uploading an object or downloading an object from S3? Maybe can we do that in the cold start phase instead of for each single invocation? So X-Ray can give you a very good overview of what's happening inside your Lambda functions. And if you've noticed in the last couple of months at reInvent 2020, there were two very important announcements related to performance, related to cost. So the first is that now you can use up to 10 gigabytes of memory in your function. And we will see in a second why that is important for performance. But of course, that also enables a lot of use cases where you actually need a lot of memory. Think about if you need to ingest a lot of data or keep it warm in memory, if you need to load a machine learning model in memory and you need 2, 3, 4, 5, even 6 gigabytes sometimes, now you have up to 10. The 1 millisecond update is very important for cost as well, especially if you used to have a lot of functions that used to execute or still execute for less than 100 milliseconds. Because what happened before is that all the execution costs were rounded by 100 milliseconds. So if you executed for 60 milliseconds, you are paying for 100. If you executed for 110, you are paying for 200. Now, the good news is that's not true anymore. Now, you pay for each individual millisecond. So if you execute for 10, you pay for 10, not for 100 anymore. Which means, in some of those cases, for example, if you're executing for 10, instead of 100, that means that your Lambda cost all of a sudden is like 90% smaller, which is good. So since December 2020, so already for 2 or 3 months, you should already see some of these changes in your AWS Lambda bill. So have a look at that. If you haven't noticed, go and check it out. But this also has an impact on the way you decide to fine tune and cost optimize and performance optimize your functions, because there were a lot of cases before where you were just a little above the rounding, like 105 or 110 milliseconds, and you really wanted to get down to 99 or 95 because you wanted to halve the cost of your function. And sometimes this was a struggle. There were a lot of techniques that I can still show you how to squeeze every single millisecond out of the performance, but in theory, and actually also in practice, this is not as important as it used to be, let's say 6 months ago, because now you really just pay for the exact milliseconds of execution. So I think that's good news for everyone. Another interesting news that happened recently, this is also from late December, a couple months ago, that AWS Compute Optimizer is now able to recommend you the optimal Lambda configuration. And we'll get to that, what that means and so on. But basically, what you can expect is for each Lambda, if you enable this, it can give you a few tips about, is your memory over provision or under provision? What is the suggested memory configuration? And we'll have a look at why this is important in a second, but very high level concept here. If you give your functions more memory, it's not just RAM, it's not just memory, it's CPU, it's I/O throughput, it's network bandwidth, it's everything. So I like to call that power. So more memory means your function is more powerful and has a high chance of executing faster. So even though providing more memory makes it more expensive per millisecond, it might run in fewer milliseconds. So you as I was mentioning at the beginning of this presentation, you might get faster and cheaper at the same time in some cases. And this compute optimizer now is able to recommend you and give you a few tips on this matter. I cannot remember. Sorry, I need to double check if in pre, I'm totally sure it will be evolving and providing even more insights. But if we haven't tried it, give it a try. So when it comes to performance and in general optimization best practices, I like to divide best practices into two different buckets, two different categories. The first category is all those best practices that help you with cold starts. So everything that happens before your actual execution. There are a lot of different ways you can minimize that. Why do you want to do that? Maybe because this function is very customer facing. It's an HTTP API, and you want a lot of users, a lot of clients to experience a cold start. Maybe the first time they hit the website, or if we have a very high spike of traffic on your website at some point, a lot of those customers might be experiencing a cold start all at the same time. And in some cases, this is totally okay. In other cases, you want to minimize that cold start to improve the user experience. So for example, you can avoid monolithic functions. That's everything you can do to minimize the size of your deployment package. As I was mentioning, the first thing we need to do is to download your deployment package into the EC2 machines that are running under the hood, because it's serverless, but there are still servers and we need to move data on the network, and every byte counts. So if you have a 10 megabyte deployment package instead of 10 kilobytes, that will take a lot longer to be transferred over the network. So everything you can do to avoid these monolithic functions that do a lot of things and that are very heavy. Maybe they're using a full stack framework or a lot of routing configuration or very heavy libraries, even though you don't always need them. Everything you can do to reduce that deployment package size is great. A very simple way of thinking of this is try to go towards the microservices or even nano services approach. So every function is only doing one thing. And if you go into that direction, you don't need a lot of libraries. You don't need a lot of dependencies. Most of the time, you just need 10, 20, 50 lines of Python, JavaScript, Java, whatsoever. You don't need 1,000, right? And a lot of libraries and a lot of dependencies. You can also minify or uglify your code. This also helps. If you're using Node.js, you can use Browserify or Webpack or all those magic tools that allow you to really shrink and get rid of all the code you're not using. That also helps. Again, even 100 kilobytes might be useful to save a couple of milliseconds, right? Optimizing dependencies, this is very critical. And again, if you don't need a dependency, get rid of it. But there are also particular cases where you can actually optimize the way you use or the way you import dependencies. For example, with the SDK for Node.js, the version 1, I think now version 2 is much better. I haven't tried it, but there is a way, for example, to import a submodule of the SDK, and that can save you up to 100 milliseconds. So if you don't need everything, if you only need the DynamoDB module or the S3 module, just load that one instead of the whole thing. There are cases where you want to keep alive a connection using the SDK. If you know that you have to do 2, 3, 4, even just 2 queries to an AWS service, in a row, or even in parallel, if you can keep the connection open, pretty often, most of the time is actually spent, all your CPU time is spent on opening, encrypting the connection, and blah, blah, blah. So there is a simple way to configure the SDK to keep alive the connections. And that works even across Lambda invocations. So you can keep connections alive and you don't pay for it. So why not? Lazy initialization is something useful. I'll show you an example in a second. But basically, if you're like me and you're a bit lazy sometimes, and you like to have multiple functions, Lambda functions, Lambda handlers in the same file because it's nice, it's convenient, you can reuse stuff more easily, and maybe your project is not that complex, so that's totally fine. It happens pretty often that different handlers, different functions in your file will need different libraries. but then you are initializing all those libraries at the top of your file, and basically you are summing up all the cold start of all the handlers that you have in that file. I'll show you an example in a second, but that can easily be avoided either by splitting one handler per file, problem solved, or by lazily initializing the shared objects only when you need them. So I'll show you a coding example. And provision concurrency, that's also fairly new. It's been out there for a bit more than a year now, and it allows you to provision concurrency. Basically, you can say, hey, I'm going to need, okay, I estimate that I'm going to have 100 concurrent API calls at some point in the future, maybe in an hour, maybe in 20 minutes. And so I want to pre-provision some Lambda runtime, so they are all warmed, just waiting for an API call to come. So that's super useful if you have predictable peaks, for example, or if you have a very sustained load during the day, and then you want to make sure at least, I don't know, 20, 50, 100, even 1,000 runtimes are always warm at your disposal. Let me show you an example of that lazy initialization. So here, for example, I have two different handlers, get objects handlers using S3 and get items handler using DynamoDB. So if I were initializing both clients up here, I would be summing up the latency. Maybe it's less than a millisecond in this case, but imagine that instead of the S3 client or the DynamoDB client, imagine these are huge libraries, or at least complex libraries that take 20 milliseconds to just initialize the object. So by lazily initializing them inside each individual handler that need them, I'm minimizing effectively the cold start of each individual handler, of each individual function. And as I said already, if you don't want to do any of this, just get rid, just split one function per file and you're good. There are other cases where this is not a great idea also. If you are using pre-provision concurrency, you want to make sure that you initialize everything as soon as possible so that your functions, once your runtime is warm, it is really warm. Because in this case, we are lazily initializing some things at execution time instead of at runtime initialization. So this makes sense, but really there is a better way to do it. So my suggestion is just use one handler per file and you should be good. I mentioned optimize dependency usage. So for example, here with Node.js, if instead of requiring the whole SDK, you just require the Dynamo SDK, you can get up to 100, 125 milliseconds faster. The same holds for the X-Ray SDK. And there are ways where you are using the X-Ray and the Dynamo SDK together. So they might sum up as well. So there is a very nice article. It's getting older. It's from 2019 from our serverless hero, Yan Cui. But have a look at this if you never looked at the number. It's really fascinating, especially if you're using Node. If you want an even better way, just give a try. Have a look at the new JavaScript SDK. I think it's version 2. And I believe it's solving this problem already for you. It's much more modularized. And this way you can avoid to do all these tricks and workarounds. Provision concurrency, we already mentioned what it is for. Basically, it's to get rid of cold starts in a managed way. A lot of developers used to do like CloudWatch alarms or CloudWatch events every minute or every half an hour just to keep their functions warm. That is okay if you just want to have one or maybe a couple of warm runtimes because your application has a very infrequent traffic, very low traffic. There are cases where, I don't know, imagine that you are managing a live sports website where, at some point at 8 p.m. on a Saturday, there is a soccer match or a cricket match or a football match. And 10,000 people will jump on your website all together because they want to get real-time updates. And in those cases, it's fairly easy to predict that there's going to be a peak in traffic. And maybe based on historical data, you can also predict how many concurrent API calls you're going to have per endpoint or per function. So you can pre-provision these runtimes. You can even configure auto scaling to make sure it goes up and down. It doesn't need to be stable for hours or forever. Keep in mind there is a ramp up time. So if you say I need 1,000, it's not immediate. It might take a couple of minutes. As far as I remember, it's about 500 runtimes per minute. So if you need 5,000, it might take up to 10 minutes, right? If it's a predictable spike, it should be fairly easy to pre-provision these runtimes, half an hour before, 1 hour before. Also remember, this is not for free. I mean, it's great and you can improve the user experience. Also remember that at that point, you're not only paying for executions, you're also paying for time, for idle. If you do this, if you enable this and you have it running for 2 hours and there are 0 invocations, you're still paying for it. So make sure it's worth it in your use case. Make sure it really allows you to improve the user experience because otherwise you're just doing what Lambda was supposed to be solving, right? Not paying for idle compute time. So
a quick question, Alex.
Yes.
Yeah, so this provision concurrency, if we enable, then even if the Lambda is not running, we will still be paying for it, is what it's saying, right?
Yes, there is a time, I cannot remember the exact number, but there is a time-based price. If you are handling a huge spike or a worthwhile spike, cost-wise, it's worth it. There are even cases where it might even be cheaper than paying only per executions. But yes, if there is no traffic and you have provision concurrency, you're basically paying for idle. Yes.
But the problem is it's ironical, right? It goes against the whole concept of serverless, right?
Yeah, it's for a specific use case. It's not like you keep it up 24/7 just in case. It would probably make your Lambda function cost much higher than it should be, especially if your application is still low traffic. Yeah.
Yeah. Okay. Cool. Yeah. Please carry on.
Yeah, that's a good point. Then there is the second category of optimization best practices, which are about all the other, warm executions. The largest majority of your executions are not cold start. So let's focus on those. There are many cases, for example, where you have orchestration in your functions. You call an external service, wait for the response, and then you invoke S3, and then you wait for the response, and then you invoke Dynamo. And there is a lot of orchestration of different things happening in parallel or in series. And usually if you have orchestration inside a function, it means that you are paying for a lot of waiting time. And the best way to improve for cost here is to externalize all that orchestration into another service, for example, step functions. In step functions, you do not pay for waiting time. You do not pay for idle. So for example, if you need to fetch an item from a DynamoDB table, or if you need to wait 10 seconds and then do something, you're not paying for those 10 seconds, which is great in my opinion. You only pay based on the number of the transitions in your state machines. Step functions allows you to visually define a state machine with an initial step and parallel or serious steps, and then the execution ends at some point. And you can have an execution spanning up to a year. So you can say, and now wait for 2 months and then run this function. And you're not paying for the idle waiting time of those 2 months or 2 weeks or 2 hours. This is great for orchestrating multiple services or multiple function executions, but also for maybe integrating for example, human interaction. Okay, now I send an email and then I wait 2 hours until that human clicks on a button or changes something in the database. And then you can continue the workflow after a couple of hours. Another interesting way of optimizing is this idea of transforming data instead of transporting. So it's very useful where when your executions already have everything they need in the event. So for example, if you use native triggers like S3, you get all the data you need in the event, and then you can use the data to manipulate or to do something useful. If you need to actually fetch the data from S3, sure, you have to invoke S3 and fetch all the data. But there are a lot of cases where you don't actually need to fetch a lot of data. The best thing you can do is to delegate that. Similarly to how you do with databases. When you talk to a database, you don't fetch all the data and then do the filtering at the application layer, right? You submit a query with some filters, maybe by ID or by filtering on a column, and you let the database do all the work so that you can fetch only the data that you need, right? And you can do the same in other use cases, also using S3. If you're fetching a large object from S3, you can use, for example, S3 select to only fetch the data that you need from that object. And by delegating that, you are spending less time fetching the data, maybe, I don't know, 10 kilobytes instead of 10 megabytes download from S3. That's a huge difference. And then you don't need to do a lot of data manipulation on your business logic because the data has already been filtered and manipulated on the downstream service. That could be S3 or other filtering services or a database and so on. Another useful way to optimize for cost is discarding events that are not interesting. What do I mean? Imagine that you have an S3 triggering Lambda, an S3 bucket triggering Lambda, and your Lambda functions are triggered every time there is a new object on S3, but you only want to be able to process PDF files because that's your application. And I see many developers that go and add to their business logic, okay, if the file is not a PDF, raise an error. And that's great. I mean, you should have that logic in your function. But even better, you can configure that filter in the S3 event, in the S3 trigger configuration. You can say trigger this Lambda function only if the file name ends with .pdf. Okay, that way, if somebody uploads a PNG or if somebody uploads a doc file, you're not executing your Lambda function at all. So that means less cost, fewer dollars, because even if you invoke your function and it fails in 1 millisecond because it's not a PDF file, you are still paying for that execution. So try to discard events that are not interesting as soon as possible. You can do this with S3, with SNS filters. There are a lot of options when you configure the trigger to make sure you are only focusing on the important events. You can also fine-tune resource allocation. This is everything about memory, and we'll talk more in depth about it in a second. But basically, a lot of people just guesstimate or try to randomly estimate the optimal function memory, function by function, and we can do much better than that. I'll tell you more in a minute. Lambda destinations, it's not really meant to helping you saving cost, but basically Lambda destinations allows you to put the output of your function into a downstream service like SNS or another Lambda function for asynchronous invocations. So why is it on this list? Because you don't have to do an API call yourself inside your Lambda function. You know, SNS.publish message might take 10 milliseconds to run. And if you can delegate those 10 milliseconds to the Lambda service, that means you're not paying for that execution time. So it is, in a way, one of the many ways you can, take away a few milliseconds of execution from your Lambda functions. And it also means that you don't have to write that code. So less code to maintain, a few milliseconds you can take off your execution. And the last item here on the list is retry policies. Keep that in mind. It's not a way to save cost, but if you don't have it in mind, you might have retries that you don't need, for example. So since a couple of years, you can configure how many retries your functions have, especially for asynchronous invocations. If your asynchronous invocation fail, your function gets executed automatically again twice until it succeeds. If you don't need it, set it to 0. Those are executions that you don't need to pay for. Make sure you configure a DLQ or some other mechanism to not lose the data. That's useful. And remember, this only applies to asynchronous invocations, things like S3 or SNS or SQS. If it's a synchronous invocation like API gateway, okay, there is no retry. You don't want to retry in its typical server side. You will need to do the retry on the client side, right? If you're curious about step functions, about orchestration, just a couple more details. You define everything in JSON. So there is a visual, like a UI visualization of your state machine, but in the end, you have to define everything in JSON, which is quite okay. You can also define it in YAML. There are plugins for the serverless framework or even for SAM, AWS SAM, the serverless application model, that allows you to define it in YAML and other formats. You can monitor every single execution. You have nice details via API or via the web console. There is also another execution time, the express workflow type. In that case, it's designed for very high throughput, and you don't really get this nice visualization, because if you have thousands and thousands of executions per second, yeah, maybe you don't really need a visual, like a visualization for every single execution. But if that's so, if you need, I don't know, 30,000 step function execution per second, yeah, that's what express workflows are designed for. I have an example of the transform instead of transport data. This is the S3 select example, where instead of running for 200 seconds, this example was iterating over a few keys, was downloading each object, and then only fetching the first 8 bytes of each object, because that was the structure of the data set. By delegating that computation to S3 using S3 select, this goes down to less than a half of the execution, 95 seconds. Okay, so maybe you have a similar workflow running for 20 seconds. Okay, it might go down to 8 or 9 seconds. That's kind of the scale by using S3 select. Of course, it depends on how large are those files that you are downloading and so on. But I think it's a good example of think of transforming data with Lambda instead of transporting and downloading a lot of data into Lambda. Now, I want to focus on the one thing that does not force you to re-architect everything, and that is fine-tuning resource allocation. That's a very low-hanging fruit that you can use to cost and performance optimize your functions without re-architecting your application, without changing programming language, without using a lot of other services, or transforming the whole pipeline of your data. I've already mentioned this very fundamental idea that memory in Lambda is actually power. If you give your function more memory, you're giving it more CPU, more throughput, more networking, more everything. So let me give you an example. If you have a very CPU-bound use case, like this very useful example of computing prime numbers 1,000 times up to 1,000,000, that's not super useful, but it's CPU intensive. That's what we're talking about. If you give it the minimum amount of memory, it runs for 11 seconds. It doesn't cost a lot, but still, let's have a look at the numbers. If you double the memory, it takes about half. If you double the memory again, it takes half. Again, if you double up to 1 gigabyte, now it takes a little bit more than a second, almost a second and a half. And that is 10 times faster than what we had initially. And if you look at the cost, it's basically the same. So this is a super important idea. I don't know how to I liked it more. There is a high chance that for CPU-bound workloads, you can increase memory and at the same time dramatically increase performance, 10x difference in this case, for a very small or almost zero cost impact. And that's huge. Let me plot this for you. So in this plot, maybe it's a little small for you to see, but on the x-axis, so horizontally, we have the power, the memory configurations, 128, 256, 512, up to 3 gigabytes. By the way, 3 gigabytes is not the maximum memory anymore. You can get up to 10, but let's stick to the 3 gigabytes example here. And what you see, the two lines is, the blue line is cost, and the red line is execution time, right? So in this example, execution times, as we increase memory, goes down very quickly from 36, 37 seconds down to less than 2 seconds, okay? That's more or less a 20x improvement, not 20%, 20x, 20 times faster. And at the same time, the cost is pretty stable and then even goes down. So it's a total no-brainer. If we position ourselves between 1 and 1.5 gigabytes, we are 15, maybe almost 20 times faster, and the average execution cost is even cheaper, is even smaller than using 128 megabytes. So this is a specific example of the computing prime numbers, but I'm going to show you a few different patterns in a second. How did I get to plot these numbers and to see this very data-driven approach to optimization? I had an idea in 2017. That was before I joined AWS. I was an AWS customer, and I started using step functions, the orchestration tool, to build a data-driven approach of optimizing my functions, because I was doing a lot of tuning manually, and that was very frustrating and very boring, to be honest. Like, what's better, 512 megabytes, 1 gigabyte, 2 gigabytes? I had no idea. So I thought, I don't want to do this manually. I'm going to automate the whole thing. So I created AWS Lambda Power Tuning. It's an open source project. You can find it on GitHub at this URL. It's available as a SAR application in the serverless application repository. So you can deploy this in one click. It runs in your account. You provide your function as input, just the ARN of your function. And this state machine is going to configure your function, execute your function in multiple memory configurations, and then come up with the optimal setup for you. So if for that specific function, you would rather use half a gigabyte, 1 gigabyte, 4 gigabytes of memory, now you have data to prove your decision. So you can provide some input, for example, the ARN of your function, all the different power values that you want to test. You don't have to try them all. There are thousands of different power values. Here, I'm usually testing the most, easy to remember values like 128, 256, half a gigabyte, 1 gigabyte, 2 gigabytes, and 3 gigabytes, just because that's to give me an idea of the pattern. And then you can configure how many times each individual configuration is going to be run. I suggest something above 20, maybe 50. The more the better, because you have more statistical relevance. And then you can configure a payload. It could be a static payload or a weighted payload. So you give me 3 payloads and I do 33% each. So there are more advanced configurations too. This is the very basic. And what you get as a result of these state machine execution is that you get the optimal power, the average optimal cost, and the average duration for your function. You also get some metadata. The metadata is about the state machine itself. You get immediate feedback about how much you have spent for that state machine execution and for your Lambda execution cost. And as you can see, usually it's pretty cheap. You can run like a power tuning run for something like 1/100th of a cent of a dollar. So it's pretty cheap. Everybody can afford power tuning their functions. And the best thing you get out of all of this is a URL. It's a visualization URL. It's hosted on lambda-power-tuning.show. That's a website that I own. It costs you nothing, and it's totally privacy compliant. There is no data sharing, so it's not a database, it's not a service. It's just a client-side data visualization tool that gives you exactly those types of data visualization. Now, what's important here is the idea of the patterns. There are different patterns depending on what function you are trying to optimize. Is it CPU-based, network-based? What are you doing with your function? So let me give you some example. The typical example is the trivial data manipulation example. This was very important until a few months ago, because if your functions were running for less than 100 milliseconds, you were paying for 100 milliseconds anyway. Okay, now this is not as important anymore, because now you pay for each individual millisecond of execution. You're not rounding up to 100. But even for this kind of workloads, sometimes you can find interesting trade-offs. So usually there is no way to make these functions execution cheaper. As you can see, the blue line always grows, basically. So more power usually means more expensive. What the trade-off is about is that sometimes you do get a couple of milliseconds of performance improvement. So if you're orchestrating a complex workflow with 5, 6, or even 10 different Lambda functions after another or in parallel, you might see the benefit of saving 2, 3, 5, or even 6 milliseconds of execution time just by increasing the memory from 128 up to 256, for example. This does not always happen, and there is some noise. As you can see, the execution time sometimes is a bit noisy. It's not always decreasing. But my suggestion is don't assume that a very trivial function cannot be power tuned. Have a look at it. It will take you 10 minutes to run, even maybe 1 minute to run. And you can run everything in parallel. Usually in these functions, you have 0 API calls, 0 SDA calls. So they are super quick to run and super cheap, and there are no side effects with other services. So you just need an input event.
Alex, just a quick question here, just out of
Yes.
curiosity. So how did you come up with, did you do background running and figure out if it 128 MB takes between 2.5 to 3 milliseconds, but at 3 GB, it takes 1. So you ran different types of executions in the background and then came up with this, or how was this?
Yeah, this is so when you execute Lambda power tuning, this is what you provide as input, and this is what you get as output. And in the output, you always get a visualization URL with your own data, so you can visualize the power tuning results of your own function. And yes, your function is executing in your account with real data. If you have a downstream database, it will be using the downstream database. So in practice, it's kind of like a brute force approach where I try to run your function with different configuration and see what works better, analyzing the data.
Fantastic.
Makes
okay, cool.
Yes. So that's the idea behind it. It's very simple. It's just an automation tool that helps you have a look at the data without doing all the computation yourself and all the configuration yourself. The important point is that there is one pattern which is super interesting. That's the CPU-bound workload. This is another example of a function using NumPy. NumPy is a very popular Python library for scientific computation. In this case, I am inverting. The function is inverting a large matrix of about 1500 by 1500. It's just randomly generating it and inverting. That's a pretty computational intensive task. And as you can see from the graph, with the minimum memory, we are running in almost 7 seconds. And if we go up to 3 gigabytes, this is running in something like 250 milliseconds. So that's like a 15 times faster execution time. What's really powerful is that not only we can go so much faster, every value here is a good value. They are all faster. the best thing is that the cost line is pretty flat. Flat means that you are faster more or less for the same cost. That's great, right? It almost never happens in the history of compute that there is something that allows you to be a lot faster for the same cost. So maybe this is 1% more expensive, 2% more expensive, 4 or maybe 5% more expensive. But if this was an HTTP API with a customer face endpoint, I want this to run in less than 200 or 300 milliseconds. So I'll go for 3 gigabytes, even though it might be maybe 15 or 20% more expensive than some other options like 128 megabytes. Usually there is a trade-off. Do you care? It's true. Do you care more about performance? Do you want to run faster? Or do you care more about cost? Do you want to make your AWS bill cheaper? In my experience, there are many cases where my Lambda bill is maybe $5, but if I can spend $6 instead of 5 and be 20 or even like in this case 10 times faster, I'm ready to pay $1 more. So it's a trade-off, it's a business decision, and what Lambda Power Tuning gives you is the data to be able to take that decision consciously. And there are other cases like the prime numbers example that I already showed you before, where when you start increasing the memory, so the power, the cost actually goes down. So there is no good reason for not increasing the memory. If you increase it, for example, to 1.5 gigabytes, you are something like 20% cheaper and something like 15 or 14 times faster. Okay, that's a no-brainer. You should just go hands down on the 1.5 gigabytes. Of course, there are a lot of other configurations that we have not tested. It could be that maybe 1.8 gigabytes is even more is even cheaper or even faster. So my suggestion here is trying to find like a local optimum value and then try to increase the granularity. So for example, try 2 gigabytes or try 1.2 gigabytes and see if there is an even better option around the local optimal value that you have found. If your workload, if your function is network bound, if you are invoking an external API, for example, usually you have the opposite situation. Usually you have the execution time is flat, meaning whatever power you have, that external API will run for whatever milliseconds they can run. So unless you are downloading or uploading a lot of data, you will not see a lot of difference. So if you want to make your network bound function the cheapest, it's always 128 megabytes. There is nothing you can do about it. You can always try power tuning, but usually network bound make it as few megabytes of memory as possible. There are cases where, even in this example, where we can be something like 100 or even 200 milliseconds faster, but maybe the cost trade-off is not worth it. So look at the data. There might be a good surprise, but in general, network bound, invoking something out of the AWS region or AWS data centers does not really make sense to use too much memory. If it's an internal API, for example, if you're running a few different DynamoDB queries, also because of the keep alive in the connection, and because that API is internal, so it's an AWS API running in the same data center, most likely, there is a good chance that by increasing the memory, you can actually see a very good performance improvement, and the cost is not that different. So for example, in this use case, running 3 DynamoDB queries in a row, I might go for 512 megabytes because the cost is maybe very similar, maybe 5% more, but I'm running in 75 milliseconds instead of 300. Is it worth it for you? If this is a customer-facing API, I would say it is worth it. And then the case that I mentioned earlier, where you are downloading or uploading a lot of data, this is not super recommended. For example, downloading hundreds of megabytes from S3, but there are cases where you have to do it. So in those cases, it might be worth power tuning. And let me show you some data here. This is the first experiment I did where I was using a single thread. So this is very similar to the network-bound traditional workload where I'm just downloading data and this is pretty flat and the cost only goes up. It's not very optimal. We are running in a little more than 6 seconds. But because it's S3 and because by using more power, by using more memory, we actually get more CPU cores. In this specific downloading, uploading case, we can leverage multi-threading. So with multi-threading enable, and this is one line of code change in my Lambda function, now you do see an interesting performance improvement. See the red line is going down pretty quickly. And now we are much faster, even at 500 megabytes, so the minimum power. We used to run in 6.5 seconds. Now we are running at 4.5. So it's a real improvement with the minimum memory. But if you're ready to pay slightly more, you can be a lot faster. Now this is a bit lower than 2 seconds. So we are almost 3.5 times faster than we used to be. And if you look at the cost, it's also comparable. So sometimes enabling multi-threading can make a big impact for these long-running functions that are downloading or uploading stuff from S3 or from other sources. So don't give up immediately like I was about to do when I saw, nothing interesting here. But then I thought multi-threading, and this is much more interesting because the cost performance trade-off is really more meaningful here. So what I really wanted to provide you with today is a mental framework. What is my function doing? What cost performance pattern can I expect? Is it just trivial manipulation of data? Is it CPU bound? Is it network bound? Is that network call external, or is it an AWS API, or is it something I can improve with multi-threading? So keep these things in mind. And if you find even more patterns that are worth analyzing individually, let me know. This is my core set of patterns. And I think this will also help you understand which functions are worth optimizing while you are coding, while you are developing and designing your function. So now if you keep these 4, 5, or 6 patterns in mind, it's super simple or more intuitive to understand or to know what to expect when you run the power tuning in your account. So takeaways: keep in mind what you're trying to optimize. Is it the cold start? Is it the warm start? So the largest majority of your execution. There are different techniques. You can avoid cold starts with provision concurrency, but always remember memory is power with Lambda. So not just memory, not just RAM, it's CPU, it's network bandwidth and everything. Try to think in terms of categories. What is this specific function doing? CPU, network, trivial data manipulation, all those patterns that we have seen will have different cost performance patterns. And you can always visualize these trade-offs and picking the optimal trade-off for your business using the Lambda power tuning. So thank you everybody for attending. I hope it was useful and insightful. And if you have questions, I'm here for a few more minutes.
Fantastic, Alex. That is, really great having you take us through these things. Now, I have a couple of questions in the way this things are optimized, right? Now, there is, let's say I'm expecting a huge spike now, and for this week I'm running a campaign, so there are a lot of traffic that is expected. So we increase the memory, and then we kind of keep the balance in performance. When sudden spike happens, like unforeseeable spike happens, means how we could how faster we could configure and make the changes in production.
Well, in my experience, this power tuning process doesn't really depend on your current traffic. I mean, this is independent, almost completely independent of how many executions per second you have or how many warm runtimes you need. So power tuning is useful in general, whether you are using provision concurrency or not. It's usually about optimizing your Lambda bill and optimizing your user experience. So the fact that you expect a much bigger spike or a spike in traffic later this week, it doesn't really affect the way you are power tuning individual functions. That's why I really like the process of power tuning, because it's language agnostic. It works on every account or every region, and it doesn't depend on the scale at which you are operating. Whether you have 1 execution per hour or 200 executions per second, if you have power tuned your functions, you know that the user experience and the cost will be optimized overall. And then if you need to do even more, usually you get into those other optimization best practices that kind of push you towards changing the architecture a little bit, putting a queue in between to avoid issues or to avoid throttling. That's usually about re-architecting slightly your solution, but power tuning is quite agnostic about that.
Fantastic. Awesome. Let's see if anybody has any question in the group.
By the way, guys, if you want to run the functions and the power tuning project, I think I also have a demo for you on a gist on GitHub. So let me share it in the chat. So you might be able to
that would be
run
really
all these experiments yourself. So if you go on Gist and you find my profile, Alex Casalboni, and you scroll for a while. I mean, I'll also give you the direct link. Let me find it. Yeah, here we go. So I'll share this link. Here you find a super simple deploy script using SAM, and you find a CloudFormation template where you have the power tuning application. So you can deploy the power tuning application in CloudFormation with just a couple, 4 or 5 lines of YAML, just by referencing the serverless application on SAR. And then I also have a lot of different functions with inline code that allow you to deploy and test this function. These are exactly the prime number, the no-op, the NumPy, linear algebra, inverting matrices using NumPy. And in this case, I'm using a layer, the S3 download, and the external API. So you have all the use cases that I've talked about in a simple CloudFormation template. You deploy it once, and then you can run the power tuner with all these individual functions and have a look at the results. Maybe also use it with your own functions if you want.
Fantastic. Awesome. I think that's it from us. And thanks again, for joining us, Alex. And I will take a couple of days to edit this video and make it better and share the link with everybody. And probably in the future, I will ask anybody to get in touch with you on Twitter or LinkedIn if anybody wants to clarify something. No, it was great hosting you, Alex. Thanks a lot. Take care. Bye-bye.
If you have questions, let me know on meetup.com or wherever, and maybe I'll share with you the PDF of the presentation too. Okay?
Fantastic. Yeah, awesome. Thanks a lot. Take care. Bye-bye.
Enjoy your weekend, guys. Thank you very much.
Bye-bye.